Hey, good day everyone, it's David. I am Managing Director of RF Shop and also Black Card Technology here in Lonsdale down in Adelaide. So I've been helping with these guest lectures for, well, it's getting close to 10 years almost. Of course, it was in person in the past, and then in 2020, last year, when COVID hit, we did a lot of stuff online. We run a YouTube channel as well, so we kind of get ourselves set up for running YouTube contents. And then last year, when we shot the video for the lecture, I actually realized, well, that's kind of covering the same lecture material that we do, because what I do as an antenna engineer is we basically apply the antenna engineering principles in all sorts of places. So the intention with this whole set of lectures and examples is just to show you where antenna engineering is used. It can be either you as an antenna engineer, but probably one or two maybe end up being that kind of person. The rest of the class, or anybody basically, just get an understanding of what happens, what you're learning is useful out there, either to appreciate what gets done, or even to make better choices in terms of what product you can actually use for your final system. As well as when you have to work with the likes of myself, antenna engineers and so forth, that you can kind of just appreciate the language that we're using and where we're coming from. And then as well, if you are kind of informed, you can also help us understand what exactly is needed for a specific system. So I guess from a system perspective, the purpose of this lecture is to show you what you are learning, what the stuff that's going on in class makes a lot of sense. Even if it's hard to learn sometimes, the maths is not always pretty. Doesn't matter, just go through it. At the end of the day, when you get to a point where you can get a product from communicating wirelessly from A to B. I mean, we're used to this in cell phone world, we're used to this in Wi-Fi world now these days, so it's definitely it's a common thing. People are used to what happens, but the intention here is to not just get used to what happens, but also to use it in a better way. Now I guess stuff that's, I mean, this is 12 months since I did the previous shoot, so of course things always evolve and we get better. And on the YouTube channel, what I'm going to shoot just after this video that I'm shooting now is a YouTube video, and I will welcome you to look at our channel. Actually, of course, I'm going to ask you to subscribe if you want to. It's more of an education kind of video, which is relevant to what you are doing. So there's a company in Europe, Antenom. They basically make, I mean, you might be familiar, it reminds you of what Lego did in our childhood as well. You can build antennas, just as this example there, with a kit. Now what's beautiful with this kit is it's not just they give you a recipe and say, well, there, build this thing, put it on a machine and test it, or put it on your radio and see if it actually gives you an improvement. They actually just give you the guidelines, and they give you calculation formulas and stuff, and say, this is kind of what you want, these are the final results you need to get. And then you get a whole box. There's a whole box full of actual bits and pieces that you get, and say, well, build an antenna, play with it. So that's pretty awesome. So I'll just quickly mention that in the video. And then the other thing that I'm going to do, which is really relevant to what we're doing here, but I can't put everything that there is to say in this lecture, because otherwise it's just going to take forever, is we at RF Shop, we're really getting a lot of inquiries and traction in 4G and upcoming 5G as well. But 4G for now is the more interesting one for me, because 4G is still everywhere. 5G is upcoming, and that's of course the one that we are keen to keep an eye on, keep on learning more about. But 4G for us in the industry is the thing that kind of makes the motor run, and people still need 4G. So what we've done, and this is what I'll display in the next lecture, we designed an antenna, which is an antenna that I would have designed 20 years ago when I was still a student. I just modified it for a relevant frequency and application now. So we make two little antennas, two examples. We put it on an actual router, and we show before and after what you get. I have some pretty pictures as well to show on this thing. So the next video after this that will be on our channel in the before you actually view this for the lecture. So have a look at that video and see if you can learn something else from there. But that's a side topic. Other than that, I hope you enjoyed the lecture. Let's get into it, and I'm sure there will be questions afterwards. You're always welcome to ask me questions. Well, it's not going to be on YouTube as such, so just see if you could reach out to RF Shop, ask any questions. If you have any questions relating to what we're saying or what we're doing, other than that, there will be questions for you, and there will be a task for you to do as well. So have a good look, enjoy. There's so much to enjoy about wireless technologies in general, and that's why I'm doing this, and I hope that I could at least share some of the joy that I have, the passion that I have for this field with you as well. So see you later. Thanks. Bye. So I think the first thing to start off is really understand what is an antenna, and it's silly as it is, but Wikipedia gives us quite a good initial explanation, and that's something to just hold on to, because if you just want to get a quick snapshot, at the moment, I mean, Wikipedia can change, so it's up there, I guess. But have a read at the link that's on the specific slide here. So Wikipedia is useful, and then why are antennas important? So there's actually a nice sentence in there. The rest of the document is not so useful, but it gives you a nice summary. Put simply, the antenna is a device for transmitting and/or receiving signals. There we go. So the eyes and ears of your communication system. So you think about yourself, you can think a lot, your brain is quite active, but if you can't communicate it, it comes nowhere. So if you can't write properly, you don't present it properly, the message doesn't come across. It's the same with antennas. So in a nutshell, that last sentence there, use a poor antenna and you're simply not going to get your call through. This is obviously referring to specifically older days when you were communicating by voice, but that's in any way true. So you can do a lot of processing in your brain, but if you don't have a way to communicate that, to convey the message, it won't get there. So no matter what application you're thinking about, if your link is not there, you have nothing. So I'm just going to go through a heap of examples just to get you an appreciation. So the first one is, of course, the one that's quite dominant, has been for the last, let's call it 20 years or so, even more. It's pretty much the cell phone market. So there's a nice picture showing evolution of the mobile phone. Now this picture I've used on this lecture for quite a few years, so that's old as far as the latest and greatest is concerned. But you could see, if you look at the actual antennas on there, at the beginning there was big phones with some external antennas, and then they gradually moved to smaller phones. And I remember, because I'm old enough to remember those days, that when they started to introduce the antenna-less phones, people were very excited, because in the consumer space, people did not want to see the antennas anymore. And there was, at the time, a perception that antennas are not necessary and not being used. But meantime, the antenna engineers involved just had to find more and more creative ways to hide the antenna inside the phone. So they got better at that as time went on. But it's always going to be the case that a smaller antenna, compromised or sacrificed design, is not going to be as good as the original antenna. And we're working with physics here. So the thing with physics is the fundamental version is probably going to stay the best one for a very long time. Whatever you do to make it smaller, more compact, or to add extra features, you will have to give something away. And that's where this picture that I show there with the Samsung with an external antenna kind of shows you have this great phone, you have a great 4G phone, blah, 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 everything is good and well, but then you need to put an external antenna on to really get the range, to get better connections and so forth. So you can run, but you can't hide. Antennas are there, and they are definitely a very important feature. Now, that the voice is the key thing, but that is so much less and less a feature. These days it's more about data. You would know more than I. You're looking at this on your computer. So it's just showing how things have changed, and we're changing along with it as well. So it's just the device, the service on the antenna connection is no longer just voice, and it's more data, mobile internet, and definitely we as RF Shop have experienced a huge surge in interest in getting better 4G or LTE connections at home. With this whole lockdown we are experiencing, or have experienced, that suddenly people realize they need to be connected, and the only way to get the connection reliable is through an external antenna. So this is certainly one key thing, and it comes to the next slide as well, which is there's a remote rural cell phone tower in the middle of nowhere, or it could just be on a hill in the city, like in the suburbs, wherever. And then that gets connected to your home. There's an antenna on the base station, there's an antenna in your phone, and that connection in between is what you need to get whatever you want to do, YouTube or Netflix or proper work done. It all goes through the same concept and idea. Just showing a screenshot there, as you could see the kind of throughput you can get through LTE is anyway fabulous. And from an antenna perspective, we have seen, I mean, we talk about range all the time in these verbal communications, but range equals stronger signal. Stronger signals and better connection quality equates to better throughput. So you get a faster internet connection, you get lower latency potentially. And that all comes back to, if your antenna is better, if you have a really good antenna, you can improve all those parameters that you as an end user expect to see. And we see a lot of customers who, they just use a website like this that I have on my screen there, speedtest.net. They just use that as their reference. And that's fine, because it's fine because that's the end user's perception or version of what is happening. But us as engineers then have to know, okay, that's your end result. But to get to that end result, there's all these things that needs to happen. And us as antenna engineers play just as a relevant role as the 4G guys or the signal processing people. And then connected life, which comes down, again, I mean, you see it's progressing through the same thinking. Customers, users, professionals, everybody is just so used to connected life these days. You can like it, you can love it, you can hate it. It doesn't matter, but it's still the reality of life. So showing a laptop, because that's pretty much everybody brings, not as necessarily a laptop, but they bring their phones along. You want to see, just quickly look something up on Google. How used are we not to just quickly looking at something? Weather, forecast, data, YouTube, Netflix, you go camping, yes, sure, it's nice to spend outside for a long time. Most of us would think, well, that's a good idea, get away from it all. But after a while, once you have young kids or so, you do want to have some connection. So people are actually wanting to be somehow connected. Maybe you need to be. So yeah, even if you're on this yacht, which I wish I could say that's my yacht that I have, but ain't happening, not yet. Anyway, so on water, if you're out in the middle of the outback or somewhere, just to have a connection for safety reasons or entertainment reasons, all the same, you still need to be connected. The only way to be connected there, you can't plug it in. You need your antenna to have a wireless connection. And what we're seeing more and more is just that picture of a shed, but basically that even if you have this big yard, the shed needs to be connected, either just for controlling the lights remotely, which could be a wireless connection. There's ways to connect cables in, but there's a big interest to just have a shed suddenly. So here's your house, there's a shed, and then as you go, there's a wireless connection, which is now quite possible these days. So you have Wi-Fi in your house on this side, and then it just takes an antenna and some additional routing or router or some device to have an internet connection in your shed. That's all it takes. So for $200, $300, you suddenly have internet connection here, not just a single device, not just one device that's good enough to pick your internet or your Wi-Fi app from your house, but suddenly this thing can have its little sub-network. So suddenly you can have a few devices connected in your shed. And we're getting that more and more, and that's also another wireless connection. So at home, it becomes more relevant, more interesting. So connected lifestyle, it's getting more and more. So, I mean, I guess many of you would be in your early 20s. So by the time you hit 30 or 40, or my age, things would be even more connected than it is right now. Then entertainment, the next slide here. So just basics, TV, radio, streaming. You can think, so of course, when I started these lectures, I looked at my first slides 8 years ago. There was a lot of focus still on free to air, so everybody had one of those Yagis, and a lot of talk about just having your TV antenna up and running, and we still do. I mean, that's still there. Radio the same, that you are used to listening to FM or AM or just those. Well, I would say basic. It's not really basic, but it seems like it's just having a broadcaster send their signal over the big transmitter and you receive it on your TV. Of course, again, streaming is becoming more and more relevant these days. So you get your internet potentially through NBN or cable, but if you are mobile or portable, you want to move around, you want to have your Netflix on your phone, even if you go somewhere else, that comes to this again. So in the 8 years that I've been doing these lectures, even the picture here has changed a lot. So you just can't stop thinking about these things. And then, of course, satellite TV, which is that satellite I showed earlier. That's kind of where it all starts from. So that's space or connection to a satellite. You can't have a cable run up there. So it has to be a wireless connection. And you need to, the distances are significant. Those small CubeSats, they are about 500 kilometers up above you in the low Earth orbit. 500 kilometers radio link. That's, you need to do some engineering work, both on the antennas and everything, to make that connection work. Because we complain if you have a 4G connection and you say, oh, I'm 5, maybe 10 kilometers away from the base station, I can't get a connection anymore. Imagine the low Earth orbit, which is L. L is low, so that's so it's very low. 500 kilometers. So you need to do some really good engineering to get a connection with the antennas and everything involved from here to there. And then it just goes higher, like you talk about 30,000 kilometers up. So, space is one to look out for, and I missed that. And I can't believe I missed that in my slides, but that's why I'm just calling it out again. Space. Now, wireless applications, mobile radio, maybe not thought about that much, but if you think about any of the emergency services, and fundamentally it's probably the most important service around, because if they don't exist, we have big problems. Just as human beings, we have big problems. But they need to react fast, they need to react anywhere. They don't have the luxury of being connected through a cable, because the emergencies will be here, then there, then there. If you think about CFS, with all respect, they're in the disastrous areas. They only find themselves in hotspots. So they only find themselves in a pickle. You need to have a good radio system. And a radio system comes back to an antenna system. So that whole network is wireless. Antennas everywhere. And that's the only way they can connect and communicate. So you can imagine the importance of having a reliable system, a good system, good design principles. If you then were to say this is just a piece of wire, you're dead in the water before you even start. You have to really appreciate the science that goes into these things. And then, of course, the ambulance is the same thing. That unfortunately everybody will one day have to deal with it, either as a bystander or ourselves, and you just don't want to have any risk in trusting that their radios are working, that they don't know where you are, or when they're on their way back to the hospital they can't communicate and say, get ready, this is a patient coming in. You just don't want that scenario. So antenna design, and police and police and fires as well, fireys, that's the Australian word, so just the fire services. And then the middle one, that's actually a project I was involved in when I was working as a consultant for a consultancy in the city. Our radio network is just a national park, so where there is a national park, and yes, that's Uluru at the back, on the back there, you're not supposed to have any infrastructure in this area because it's a protected area. It's so remote, there's not much access, there's not really enough justification to bury cables and to go all crazy, because every meter you dig a hole for a cable is expensive. So you just get a pole up, get an antenna from one point to the other point. You're talking about suddenly having a 20-30 kilometer reach from one point to the other point with 2 antennas. Think how much cheaper that is, how much faster you can have a connection. And then you have the service. And there comes tourists, international tourists, Australian tourists. They need to be safe, and they need to be able to communicate back if there's a problem. And our network operators won't just say, well, just put up a cell phone tower there, because there would only be, say, 100, 200 users. It's not worth it financially. So you need to have some other system. Antennas. It's all about antennas and wireless RF connections. Now, if we are lucky enough to fly again, which currently is not the case, but that's just beside the point, and you can imagine the amount of wireless connections needed to get an aeroplane safely up in the air, safely from point A to point B, and then safely back on the ground. That's all different systems and different wireless connections. So first of all, there's the photo on the left. You see those orange lines, and you could see it if you go to Adelaide Airport. You drive around Tapley's Hill Road, you'll see those antennas, just a whole row of orange things standing at the end. You wouldn't know what it is unless you, think about it and kind of had a look at it. And they are actually antennas that's part of the landing system, and they're at the end of the runway, and they would guide the aeroplane. You see that cross at the bottom picture there, there's a cross. So basically the aeroplane needs to know how high it is as it comes in. You don't want it to come in too steep, and you would certainly want to be sure that it is aligned with the runway as it comes in. Those glide slope systems and the ILS systems, they're all antenna based systems that needs to be designed properly and put in place properly so that you can guide the aeroplane into the correct place to touch down at the right angle so that it doesn't crash down, and that it doesn't come at the wrong angle and just skids over the runway. So all those little intricacies involve somebody who has a better understanding for antennas than just the software behind it or the coding or the hardware engineering behind it. And then, of course, the navigation itself, which is just GPS satellites. So not just GPS satellites, but you need to know where it is, and it needs to know what direction it's heading. It has its own electronics to tell it, but also with GPS, it also has a relative positioning. And so there's a global system available, communicating wirelessly to communicate to the airplane or any device. I mean, GPS, we know it all. We just put our phone on, we have GPS information, we know where we are, and we're happy. But that's actually not just a matter of, oops, I am here. There's all wireless communication available, involved to get that information through to your phone that you just see as a picture at the end of the day to say, on Google Earth map, boom, that's where I am. And if you were to tell me, yeah, but what about assisted GPS? That is, again, wireless connection. So assisted GPS, I'm not expert. I used to deal with this a little bit when I worked for Dell Computers for a while. GPS itself gives you the basic signal. So there's ephemeris data from the GPS antennas, satellites coming down. So there's communication happening up and down between you and the your phone and your the GPS network to tell you where you are. Assisted means there comes extra information from the base station. So you actually connected to the internet through a 4G network or a 3G network. And there's also information, because then already the system tells you, well, I know I am here because this is the tower I'm connected to, plus there's other towers around. So if you have a tower here and there, and you see all three of them, you're probably in between them. Or if you are further away, you see this one, this tower, but the other ones are much weaker. So already the system can narrow you down. So I have a good idea where you are, and that information can then go up to the satellites as well, and the whole system knows, right, I narrow it down now, this makes my life much easier in trying to figure out exactly where you are. And the time to get to a fix, to know where you are with assisted GPS is significantly faster. But the point being, that's a wireless connection. And if the antenna wasn't good, imagine. Now, if I were to go back to the slide, let me just jump back again. I can. Can I? No, I can't. It doesn't allow me. That's fine. Okay. The picture that I showed about the cell phones not showing any antennas at all, it's actually deceptively simple. Because if I take my cell phone and I just hold this thought, just pause for half a second. Okay, I'm back. My phone, this is an iPhone 10, so I guess by now it actually feels like it's an old phone. It has GPS, it has 4G, but it covers all the Australian bands. So the 4G antenna is not just a silly little antenna, it's quite a complicated antenna. It can do MIMO, so there must be more than two antennas in there, or two antennas at least, two 4G antennas of some sort. It has Bluetooth, so it must have a 2.4 gig antenna in there. It has Wi-Fi, dual band Wi-Fi. So there must be a dual band 2.4 and a 5.8 gig antenna in this phone. And that's all in this device. That's very complicated. So as a user, and even as I'm sitting here, I was just thinking about it out loud. That's quite a lot of compact features into one little device. So there's a bit of engineering in this. And I mean, I'm not endorsing any specific brand. The previous photo I showed was a Samsung, so I have my preferences, but it's just by being used to it. But the level of antenna design complexity and quality in these devices is really good. So the next one is just basic network backhaul. So this is going into potentially into detail, but it actually is quite simple to explain what these guys do, and that's just wireless or network backhaul or point-to-point links of any sort. So I'm not going to jump into specifics there on this slide. Don't have to worry about what am I saying, like it's TDM and it's Ethernet 100 and that OBGD optical fiber. That's all systems that exist, but the most important one for us here is the top, to show two dishes facing each other. So between two dishes, and it's the same as what I mentioned earlier about the Uluru National Park, two dishes connect to each other, and there's a lot of data that can come through. So you're talking about 100, 200 megabits per second kind of link that you get between those systems. It's a whole field of its own. So people call themselves RF engineers, and then that's actually not clear what they are, because they're specialists in microwave design. I've dabbled a little bit with this also in that consultancy, and I've just seen there's a lot to learn and a lot to appreciate. But that's, again, gets used in backhaul systems. And if you were to look at the Westpac building in the city, just look at the roof. You'll see how many antennas there are on the roof. And they are all either 4G antennas or other systems, and there's also dishes on there. Those dish antennas would point to another dish somewhere else. So you have two dedicated antennas talking to each other. That design and the fact that they have certain distance between them. And again, you talk about 30, 40 kilometers easy on these antennas. That's a wireless connection, high speed, and it's suddenly it's tower here, tower there. Of course, it takes a while to set it up. But you have a high-speed connection between 2 points, and there's nothing in between that you need to do. You need to work on point A, you need to work on point B. You need to make sure there's a link between the two. But the quality of these dishes is significant, because those dish antennas, which is really a parabolic reflector, plus components in there, there's a lot of design. And you could be either a microwave engineer and you just use the antenna, and you need to have a good understanding of the RF, or you can be an antenna design engineer and you actually build the dish itself, and then you don't know where it gets used. Both areas are relevant to knowing and understanding what the antenna actually does for you. There, of course, radar is one that gets used a lot, and the examples I have here is more or less military focused, because it's not something that you know a lot of unless you're actually in it, and I'm not in it, so I know what the principles are for radar. But there's different types of radar. The big thing how it works is, in a nutshell, you send a pulse, you see what comes back, and that is basically a way of detecting what's going on. So you could see the examples that I have there is just some setup. So the airplanes would fly around an airport, and the radar would keep sending pulses and see where the airplanes are around it. An airplane itself would also have some form of radar. The photo there of a Lufthansa airplane is a weather radar. Again, it would send out information, or it would send out a signal, and it analyzes the information as it comes back to see what it could make of that. And that's, in this case, taking the information and building a weather picture of what's ahead as the aeroplane flies. There's a lot of information coming through from other devices as well, but for the airplane itself, it also needs to see what's going on, because if you're on the front line, which is that you need to make sure that you see exactly what people say. When you can't fly blindfolded and just listen to the rest of the world and trust everything that's going on, you need to have your own set of eyes as well. And this is what this radar is. It sends a pulse, looks at what comes back, and then analyzes the data. I just found something yesterday on the internet which I thought was useful to show the radar when you look at stealth fighters, and that's obviously so cool to watch these days. If you see all these airplanes with their funky shapes, and they have all sorts of corners and angles and shapes that are specific. So this picture kind of just shows you how that works. So on the ground, if you have a commercial airplane like an Airbus or Boeing or something, you actually want people to see you, because you want to tell them, I'm here and this is who I am. So you don't care about any radar profiling. So on the ground, there would be a dish of any of these types of antennas that you see there. sends a signal, and it looks at what reflects back. These round shapes, they just bounce everything back. So you see a massive reflection coming back from this. You send the signal and you see what comes back. Say, well, I see there's an aeroplane, and then by all the analysis of the data and kind of profiling how the airplanes look and should look, they could say what it is. Not just there is something. They can actually say, well, it looks like an Airbus, blah blah blah. So that's another significantly interested, but very well, to me it's quite complicated, but I really find it amazing to see what the radar analysis specialists do. But now the other picture there, stealth design. You can see the shape is totally different to a commercial aeroplane. It has sharp edges, so all those surfaces, they reflect back, or different, no, they don't reflect back, sorry. Ignore what I just said. Those aeroplanes try not to reflect back at all. So there's a signal coming in, but the shape is such that it bounces everywhere. So the incoming pulse just goes, it spreads everywhere. Very little, if anything, comes back. So this guy who's trying to see what's going on, he can't see it coming back. So that's the technique they use, and it's kind of very basic explanation of how it works. I mean, I even think people would look at this video and say, well, you don't know what you're talking about. There's an element of truth, because it's the principles that matters here. So that's if you ever wanted to go into that field, it's really fascinating. Now the next one, I used to work for a company called Coda Wireless in North Adelaide. Well, they moved meantime, but anyway, so that's the topic there is connected vehicles. So of course there's an interesting focus to go into vehicle to vehicle, which is V2V, vehicle to infrastructure, or autonomous driving. It's also the big buzzword that's coming up these days. So it's a connected car. So in a very basic nutshell, vehicles can communicate to each other, if it's just by saying them where they are. So I am driving here and I'm going in that direction and I'm at this speed. The other vehicle does the same. So even if you are driving, the vehicles could have radio signals that transmit a bit further than your eyes could see. And not much. I mean, you're talking about maybe a kilometer or so, but imagine your car is driving and it has intelligence about all the other vehicles around you. And this is one of the things that the example at the bottom there shows, that you're going around a corner. Somebody's driving around this corner, somebody's coming up this corner. Both vehicles tell the other one, I am driving at 60 kilometers an hour. And they both say, oh, actually we're coming to the same intersection. And suddenly one car would say, hang on, you're not slowing down. And the other car says, you're not slowing down either. So then both drivers, before they could see each other, say, there's something wrong here, because this guy is supposed to start to slow down, or somebody's supposed to slow down. And then all it does is just says, well, there's something wrong here. And it gives that alert to the driver. Autonomous vehicle would then go further, and that's a whole different discussion about what's the vehicle going to do. We're not there yet. That's, as far as I am aware, that's a very risky thing to do, is trying to take over, because the driver might actually know something that the computer doesn't know. But when I worked at Coda Wireless, what these vehicles would do is just tell the other one, something is wrong, you need to act. That's all. Just gives you information. What you do with the information is the next thing, but it just gives you information to say, there's something on your right, it's not looking good. That could be a difference between taking action or not, could be significant. And that's the kind of thing that happens. And there's another example there, that you are behind this big truck. So you can't see anything, but then there's a car before and a car behind, and you are behind this truck. You can't see anything, but your vehicle knows there's a vehicle there, and it can see cars coming on. So, the situational awareness, which is all it's constantly moving, and because it's constantly moving, you need that wireless system, and hence the antennas around that as well. The next thing I just wanted to touch on is the parameters for antennas. Now, it's a difficult topic for me, because when I did the lecture in the past, I could see a lot of loss of interest if I start to go down this path, which is understandable, I guess, but it's still important to me to just have this out there. So I'm first going to just go through the few basics, just to say, well, these are the words on spec sheets, data sheets that you would come across. You probably want to know about them and just be aware of them. and then I'll just go through the list again, just adding more detail, and to see if it makes sense. And I'm asking you, I'm not just saying this is it, I'm just take this slide and kind of try to remember what these are. And then when I go through the design example, I will use these words just to say, well, this is the word, this is the relevance to that, and this is kind of where it goes on. I'm not going to go through the whole list, but it's just the principle. So the first one is antenna gain. So it's a matter of how much the antenna adds value in a specific direction. And I have in my video, when I talk about omni antenna, I actually have a balloon to show an example. So I won't go into detail, but there's a word to remember. Radiation pattern goes hand in hand with gain. It's not the same, but it's very much related. And you need to, if you know one, you can assume something about the other one. It's always an assumption, but if there's something wrong, if your assumption doesn't work, if something looks like it doesn't tie up, then you know there's something wrong. So the two go hand in hand, although they are different, totally different. VSWR, voltage standing wave ratio. That is, I'm using this version of that information because that is often used in data sheets. So voltage standing wave ratio is an indication of how much energy, or it interprets how much information let me try that again. It gives you an understanding how much energy is going into your antenna and hence getting sent versus how much is coming back. So a voltage standing wave or standing wave, you need to think about a wave theory. So just take yourself to a swimming pool or your bath and you drop just make a plonk or something, and you have this rippling of the water, so it just have this wave swelling. When it hits the wall, it comes back. So you can see the wave coming in and it just comes back. But because you have two waves now, you have the incoming and the back one, there's this build-up or summation. That ratio of the summation to what the original would have been is a standing wave, and that is the how would I say this? That's how you read this. Now, by the time that you actually just look at the data sheet, you don't have to worry about the complexities of what it actually means. You just need to look at the number, and the number will tell you if it's a good antenna or not. So here's something to use in your reflection. 1.5. Just remember the number 1.5 and see if you can use that in your report. I think that's just a good number. Path loss. So I said in the introduction when I was downstairs, there's a transmitter and a receiver. So you have two radios, some way or form, okay? And you have an antenna. So there's the transmitters, you have the antennas and everything along it, and then in between, there's something. The link in between is a path, and there's losses over that. The losses could be because of distance, could be because of obstructions or anything. But path loss is a reality of a wireless situation, a system, and it's something you cannot ignore ever. It's there, and that's kind of fundamentally what you need to use. Now, the last one is polarization. It's probably getting a little bit into more detail, but if you get this wrong, you just have no connection. And all I could say is if you look at your TV antennas in the suburb where you live, they will always be flat. Why is that? Because it's horizontal. So there's horizontal polarization on the TV antennas on the roof, because at Mount Lofty they transmit in horizontal polarization. So in other words, the signal gets sent through the air horizontally, then you have to pick it up also horizontally. If they were to send it vertically, and you still had the antenna like this, it's cross-pole, and there's very little, in theory, there's no communication or transfer of energy, but there would be a little bit because we are in a real life, we don't live in a theoretical world, but it would not work. So the polarization is very important, but it does go a little bit more into detail, so just something to remember, always to be on the lookout for. If you get it wrong, you have a problem. Now I'm going back to the slide, I'm going into more technical details. So gain and efficiency go hand in hand. So your antenna could be lossy, you lose gain, but you don't, it's just gone. So it's something to look at. Radiation pattern and directivity is related. Directivity is just looking at the pattern itself. So you have the shape that you create. The directivity is kind of more the translation of the shape without considering any significant losses or any artifacts that you don't have control of. VSWR, which, as I said, that's the one that's on a data sheet. That's why I decided to put that as the one to remember. But all these terms that I show here, they are actually related, and when you get into detail, more of interest. So S parameters is a tool that we use, or a kind of a matrix of the signal. So how much is that? This is in dB scale. So S parameter is insertion loss, there's a return loss. There's impedance matching as well to look out for, and that is related. So impedance matching means, is your antenna matching the cable or the system? So are they looking the same? So all I could say is, if you look at your normal cables, you might see it's 50 ohm, but your TV system is 75 ohm. So there's a difference. The two don't go together. So you could say one looks like this, one looks like this, and there's not a perfect match between the two. So there would be some interference? No? Sorry, words fail me. Mismatch. It's just the word, mismatch. So there is a mismatch, and there's going to be losses in between, because it's like a wave flowing, and suddenly it has to step into something else. And that interface from one to the other is not good. There are ways to overcome that. And that's a whole thing, is impedance matching. That's the significance here. And resonance, it's just something to be on the lookout for. And I will show you an example just now using a machine on resonance, and basically where a structure looks to be resonance as far as VSWR is concerned, and you have something you could use. Path loss, there's a lot of stuff in there, which is good. I mean, this is where it gets really fun to work on these things. Frizz equation. So that's an equation that actually you can use to calculate how much power is at a certain distance. So I send X amount of power. How much power do I have of my receiver? So you use this Frizz equation to get to that. Transmit power, receive sensitivity, losses. Those three terms are used in the Frizz equation as well, so that they can be used to figure out how much do you get. So you can think, now I have my phone again. The base station, the further I'm away from my base station, the less I can hear what's going on. My phone is starting to struggle. By using the Frizz equation and a bigger version of the same equation, you can actually see when you receive, you can calculate what you get and if that's enough or not, because the system can only hear so much and not more. If you don't have enough power here, there's nothing going to happen, and then you need to do other stuff to try to fix that. I have diffractions and reflections as well. They relate. I don't know where to put those two terms, but I thought I'll put it under path loss, because it has to do with the actual path between A and B. So you would have reflections from buildings, you would have diffractions. The two words is quite hard, and me being an English second language speaker, it's sometimes you have diffractions, which is just a little minor cut, go back. Edwin, hierdie moet ons net doen. Hierso, 9 minute 18, wil ek net verander. Okay. Diffraction and reflection has to do with the actual link. I didn't know where to put this information, but it's kind of in the path, so that's why I put it under path loss as well. So it's basically reflections, a bounce, or diffracts. These kind of things has a big impact on what you get at the signal on the other side, and it needs to be considered. But it goes into detail. So this is not something, if you're not really an antenna person, that you probably need to think about too much, but you need to be aware of the words, and if it comes up, you can at least remember this is an antenna feature, or an antenna wireless feature that I need to be aware of. Polarization falls into linear, circular, vertical, horizontal, or slant 45. Now, as I said before, the TV antenna is horizontal, so that is all good and well. Here in Adelaide at least. I mean, elsewhere in the world or in Australia, this is very likely to be different. And then there's slant 45. So you can have all these angle orientations, and you just need to make sure that the antenna on the other side does the same, and you're good. Circular polarization, that's quite funky. It basically, as it transmits, the wave turns around. So just as phase goes through, it looks differently as it propagates. I won't go into detail because that could get very confusing very quickly, but they use this in tunnels. Because in tunnels, there's all sorts of, now the word I used before, reflections. So the signal gets messy. So you try to send this perfect signal. But once it starts to bounce, it just goes all over the place. And then after a while, it just looks like this. The only way to pick up what's going on if you have a circular antenna, because a circular polarized antenna doesn't really care what the orientation is, because it picks it up. So if it's this or that, it picks it up. But was it purely like this, it looks very messy, and you can't actually pick a lot of the signal up. So by using circular, they eliminate the problem of reflections. And now this is my favorite, and I want to talk about this because this is something that gets forgotten a lot, reciprocity. I say this because this is to me important, and when I do designs, this is something that I look at. And the rule of reciprocity is the way something behaves, passive device, one way or the other way is the same. And this comes down to maths and how you look at this. So a passive device means you don't add energy. You don't, like an amplifier is an active device. You actually add energy from outside to change the behavior. So you amplify the device or something like that. An antenna is a passive device. So it just has a characteristic and it behaves like that. But you don't add any power to it. You just have this guide going through. So literally it's energy coming in, it gets manipulated and it transmits out. But an antenna is not just transmitting, it's also receiving. So what comes in, how do you understand what it receives? You use the theory of reciprocity. So either look at it from how it sends or how it receives to do your maths and do your calculations. But because of reciprocity, we know it has the same characteristics. And that is very useful because it means that you can create pictures and you can do analysis with something transmitting. And when we do pictures, which I'll show later, you can show this wave going out and it just looks good. But you know by theory of reciprocity that it would do the same thing if it was receiving as well. So that's where this is useful, and as a designer I find this one of the most useful features for antenna design. And it's sometimes very hard to understand, very hard to see. And if you just say, I know this theory works, reciprocity works, you don't have to worry about I don't get my head around this. You just say, I know reciprocity exists, it's a passive device, and I know therefore that my antenna, if I look at it this way, the other way, it has the same thing. Cool. Now, I'm going to do a demo, so I'm just going to pause the video for a while. I'll set up my demo, and I'll be back. Okay, so what I just wanted to do is show a VSWR measurement. It's not a high-end measurement, I just wanted to show what the effect is. So what I have is, I took a dipole antenna. Now, let's not go into detail. I took this antenna from a Wi-Fi router. So this is just a little dipole. There we go, I can show it there. It really is one of those typical things. It has a little bend, so it just screws in. So it's nothing fancy about the antenna. It's all pretty basic and self-explanatory. VSWR, as I said, is standing wave ratio. It's a measurement that we use to understand how much energy goes into this thing. So if I take this antenna there, I say I'll plug that in. I want to see how much goes in and how much gets radiated and where does it work. The resonance of this antenna. And that's all we can do. So if I screw this in, I'll just go this in the camera, see if I could do it in my field of view. Yeah, it's working. Just put that in the machine. There we go. So the machine is network analyzer. So the network analyzer measures over frequency. So this measurement starts at 2 gigahertz. I look at frequency there. It stops at 3 gigahertz. And you could see there's something happening here. Now, this something that's happening here is the VSWR measurement and where it is a minimum. In other words, at this point here that you see is where there's actually there's almost no VSWR, there's no standing wave. In other words, if you think about this wave again, there's a wave coming in, it hits a wall, comes back, and there's the stuff that's happening, like with the standing wave is quite high because the ratio between the minimum and the maximum is huge. This area is like there is no wall. So the wave comes and it just keeps going. And where is it going in this antenna? It actually goes in and it starts to radiate. So this antenna, at that frequency that you see there, which is 2.4 gig, just below 2.4, 2.5, 2.45, this thing accepts the energy as it comes in and it just goes. And that's what you want. Now with the theory of reciprocity, it's the same. This antenna would basically, if something comes in, it just comes in, sucks in, and that's the receiver side of the same antenna. So that's what VSWR tells you. It tells you where it works, it tells you how good it works. And I remember I set the value 1.5, so there's a line there. I just want to see my screen so I can see what's going on. There we go. There's a line there. The second line from the bottom is 1.5 to 1. We, or myself, use that as a measure to say, well, that's good enough, because that's where they basically they say that's the level that it should be. 2 to 1 is often used. So basically, there's a band there, 1.5 to 1 band, where this antenna is at least transmitting the signal, and it would pick it up if there was something receiving as well. What's interesting, and this is just a silly example, there's nothing highly scientific about this, but you would see there's a lot of activity if I move this around. The antenna has, of course, some transmission here, but as I get my hand closer to the antenna, I'll just go like that. So have a look at the screen. It just starts to do different things. It moves because my hand is interfering and it's becoming part of the antenna and it's reflecting from my hand. And that's part of the beauty of antennas is they're actually alive. They're radiating. They're transmitting energy out. So there you go. VSWR in a very short nutshell, but it's alive. So I like that stuff. All right. Next thing. So what I'm going to do is just show you a video of when I did an antenna measurement at the Adelaide Uni, which is of course where you guys are supposed to be, when it's not locked down. So I did an antenna measurement there. The antenna is it? Yeah, no, it's not. I don't have the antenna here. Sorry about that. So the antenna I measured at the chamber, but I did a whole discussion about what I do at the chamber. So here's the video. Have a look. So I'm here today at Adelaide Uni doing some measurements. It's really a bit of fun and research work that I do, not as a sideline, it's really for customers and also for ourselves to educate ourselves with antenna performance compared to the CS3 simulations we actually do. At the moment I'm measuring Zebra, so that is our directional 2.4 gig antenna that we developed. It's a 2-port antenna, so it can be used in a MIMO Wi-Fi configuration. It is circular polarized as well, so you know it has a lot of applications. So once the chamber is open, I'll show you on the inside. Just on the outside, the basic setup that you have with a chamber, this is just functionally what it does is there's a machine here called a vector network analyzer, or a VNA. A VNA does S parameter measurements. Now S parameter in our RF world is the coupling matrix or coupling numbers. So S21 means you try to see how much energy goes from port 1 to port 2, and that can be used, like in this case we actually send the signal to the back of the chamber to an antenna, and we try to, well, we see how much energy comes back through the other port, and I'll show you on the inside what it actually means. So it makes more sense when you see the whole setup. So when the measurement is done, I'll show you the inside. But what you see on the screen there, this is my laptop, so this is all work email, which is not always fun, but they're necessary evil. It's building the pattern. So this is the radiation pattern that you would get for an antenna if you ask for data sheet. In a setup like this, it basically builds the pattern. So we have an antenna and it's basically slowly rotating, and as it rotates, we see how much energy is this antenna getting, and then you rotate it further, and that's how you build this picture. Okay, so that's the inside of a chamber. Just a quick view. So you could see you have anechoic or radar absorbing material. As I go, just quickly as this turns through, I'll show you. So that's the Zebra antenna. It's just homing back, so it's going back to the to zero. That antenna there is the antenna that we test, so that's what we call the device under test. That antenna gets rotated. Now it's just basically we're just resetting the whole chamber so we can start set a new setup. As it turns, as it does there, it would stop. So the chamber would turn the antenna, it stops, it takes a measurement. So that antenna then gets a measurement like that. There you go, it's actually now at the 0 point. That antenna gets tested, so we use the VNA to see, let's send the signal through from, I should have gone the other way, that chamber there. So there at the back you see there is a there's there is an antenna. That's a horn antenna. It's a wideband horn antenna that sends a signal. So signal comes here, so you see waves coming through, travels all the way here, gets received there. And by turning this one, so this antenna turns around, as you mentioned, so you take a measurement, comes in, do a measurement, turn a little bit, do another measurement, turn a little bit again, do another measurement. That procedure, which takes about 3, 4, up to 5 minutes, because you go through all the steps, builds you a radiation pattern. The radiation pattern is then what we use to understand where does this antenna work. So in which direction did I get the most in the energy from that side to that side, and what direction, orientation of this antenna behind me, did I get the least. That builds you a picture, and by knowing that of an antenna, you can design a system and you can use the antenna. So if we say we need a Yagi antenna that's directional, we know that in that forward direction, a specific direction, it works at its best. So I want that to face in the direction that I actually want to get some signal, and then the other way around, if it faces away to the back where you would get nothing. With an Omni antenna, it's the same idea. It's just then you look for something that, as you turn it around in this chamber, so in that way there, you'd almost see the same every time. So you turn, you keep turning this thing, and as you turn, you see the same result. Why we use a radar absorbing material is you need to have a zero baseline. So you have a chamber that takes out all reflections, it takes out all the weird stuff that you get out there, so the real world stuff, basically ground reflections, building reflections, people moving, cars, all that stuff. You take that away. Now you could easily say, yeah, but this is not the way it's going to be out there. Whilst that's true, what you actually want to do in this case is have a reference. So here at Adelaide Uni, where I'm measuring this antenna, I can tell somebody that's what this antenna does in a clean environment. Somebody in the US, somebody in Europe, somebody in Asia can do the same measurement. So we all talk the same language, because if you want to only test antennas in a real-life environment, there's so many variables. So basically in a chamber like this, you take out all the noise, all the variables, you just have a clean setup where you take that VNA that I showed there. So that's the vector network analyzer. It sends something, you see how much it picks up, that gets you a complete picture. You have an antenna, you understand what you have, and you can put it on a table, and somebody from overseas can do the same measurement on another antenna somewhere else, side by side. At least all know exactly what we can expect. And then that example reference, we can put in dirty air environments, our reflections, our real life environments, and we all know what we should expect to see. That's it for now on anechoic chambers. Thanks. Now, as I mentioned, I am also having a lot of fun doing a YouTube channel. So I try to explain basic antenna characteristics and behavior on the YouTube channel. So 2 other videos that I took would be regarding typical designs. One is an Omni antenna. I'm not going to tell you now what it is, because hopefully the video explains it a bit. So the first video that I want to show you is an Omni antenna, and I'm using a balloon to kind of expand a bit about the concept of radiation pattern. So see how it goes. The idea today is pretty much just to talk about Omni antennas and how they work. Now, I'm not going to go into detail to tell you the inner workings, because that obviously differs between different antennas. I just want to cover the basic concept of what an Omni is for you as the end user. So first one is that it basically is an antenna. The word Omni means omni, everywhere. So it's an antenna that if you put it on a roof, it would cover everywhere. Now that's the good side of it. But to explain really how it works in terms of the operation for a customer, let me have a look at this balloon. So when you look at antenna gain, the first thing is gain is not actually something that is gain that's more than nothing. It is just gain as in a relative measurement. So if I have something, that's my reference, which is like a round balloon. This is my reference, what I have. Then when you want to have more gain, it means that you do something different so that it actually works better in a specific direction. So let's say there's our reference point. That's a isotropic antenna, as we would call it. dBi is 0, so that's your reference, 0 reference. What we do with an Omni, you basically, similar to this, you squash the top and bottom and just see how difficult it is with an actual balloon. The thing to watch is, that's nothing. Once you start to squash at the top, the edge just starts to go out. So with a typical dipole, which is just the most basic Omni, you would have a donut shape. So you have nothing at the top, nothing at the bottom, You can see it's a bit flatter at the top and bottom as well, but it has been squashed a little bit to the side, so you have gain on the sides, on the outer sides, and it's an Omni, so no matter how I stand, it always gives you the same performance, no matter what you look at from. Now if you have a high gain Omni, the same thing happens. You have the same concept, but you squash it more, so it goes out further, even further and further, so that could give you, say, a 5 or a higher number of an Omni. So this is the Omni that we have on our website as well. Just bring it a bit closer. You see it's a marine Omni antenna. It has 5 dB gain. So 5 dB, it's a nice number, it's not too bad. And what the difference is, this one, it radiates all around. So wherever I stand around this antenna, it gives you some coverage. It's quite broad as well, so you can have an elevation or top and a bottom view that's quite good. So basically you would have a radiation pattern like this on this side and on that side as well. What's important there is if you have this is a marine antenna, so if it's on a boat and the boat is rocking left and right and so forth, so basically it goes up and down a bit like that. If it goes like this, you still have something on the horizon, so it doesn't matter if the antenna isn't properly aligned. If you have a high gain antenna, so very flat, what means is it's like a disc, so cone like this. When you start to move around up and down like this, you lose the target. So when it's a high gain antenna, nice beam like this, once the antenna stands like this, there's nothing on the horizon anymore. So it's not always to say bigger is better, high gain is better than lower gain. You need to look at the actual application before you make your final decision. In a boat, low gain is often quite better. When you are actually, you know this is static and it's always going to be nice and upright like that, a high gain would be good enough, because then you can reach further across the horizon. Thank you. That's it for now. Now the other antenna that is very useful is a Yagi antenna. I did a video on that as well, again with a bit of balloon explanation on the concept itself. So that was fun. It was last year, and it's let's have a look how that goes. So here's a Yagi. Today I just quickly want to touch on the Yagi antenna as a concept or a specific popular antenna. Again, like before, I'm not going to go into the specifics of how they work. That's not important for this video. That's a discussion for another day. Today I just want to explain what it does for you as the end user. I'm first going to look at the Yagi antenna, which is obviously a big favorite for us. As mentioned in the previous video, it was designed or patented in 1926 already, so we're getting close to a century of celebrating the Yagi antenna by two gentlemen named Yagi and Uda. So the full name is really Yagi Uda antenna. What it does, again, it has antenna gain, quite a lot of antenna gain to the front. That's something you can manage. You can make it higher or lower, and there is obviously, as always, a design impact that gives you benefit or specific parameters that you can use. Coming back to my balloon, so 0 dB gain, dBi, 0 dBi, or my isotropic resource. What a directional antenna does, if I look at it from the back, I basically take away air from the back and I start to squash it through the front. So that's what it does. So you get this effect that you take away from the back and you squash through the front. So forward gain is what's necessary. Now, as you can imagine, the more you squash, the more you make it like that, the narrower it would become. So it becomes very pointy, like a laser beam. That's when the Yagis get longer and longer and longer. That has its benefit in certain applications, as I have mentioned my beast in my previous video. But in general applications, something about 11-14 dBi gain is quite useful. Then you still have a reasonable beam width. It doesn't get overly complicated. When you get to 18 dBi, it gets quite narrow. If you know exactly where you are pointing and you are willing to get that point where it is absolutely pinpoint and wind movement and so it doesn't bother you, fine, that'll work well. So onto the Yagi itself. This is our 4G Yagi we have on our website. It comes with a very short pigtail, so you need an extra cable to get it to your modem. On our website there is a way to get your modem set up and also what cable length you need, so that's all configurable. The Yagi itself, at the back, as you can see here, this one in particular has a big reflector at the back. Sometimes it's just long elements at the back, but the concept is that the antenna by itself, if you stand on this side, there's not much happening. So this is pointing away from anything sensible. So this is the back, so I don't want anything to do. I want to go that way, up to the front. So more elements would often make it higher and higher gain, but as a basic rule of thumb, every 3 dB extra gain means you need to go double the length. So if this one is quoted as a 14 dBi gain antenna, as it is, to get to 17, which is 3 more, it has to be double the length. So it gets quite clunky, but this is a good number. it's a good antenna. If you look at size-wise, I mean, it's about 1 meter long, pointing in that direction, so towards the camera as we look at that, or away from the camera this way, and that's the antenna that you have. So that's Yagi in a nutshell. Thanks for watching. Now, and the last video that I want to show you from an outside source is when I did test at Adelaide Cove. Now, here in Adelaide Cove, the signal is pretty disastrous at best. So the test I did was to try and demonstrate what antennas can do for somebody that has nothing to actually get something quite decent. And this is significant because it's not just showing airy-fairy antennas would be good and they're all going and well, and try to tell a story without selling a specific concept. In this case, we actually had hand-on-heart results that we could show. So this is probably one of the best antenna experiences that I had with this whole YouTube video story to date. So have a look. Okay, so what I've done, this is basically in here in Adelaide Cove, there's next to no signal at all. My modem is standing here. As you can see, the cables are not connected, so this thing is in auto mode and it's just doing what it's able to do here in this specific spot. So you can think the residents around us, this is kind of the thing that they would face every day. If I just do the reading here, I took a screenshot as well, I'll just do it again. What you have is RSRQ is minus 12, not great. RSRP, that's a single strength, minus 123. So that really is where the problem is. There's just no signal here at all. So let's just go to speedtest.net and see what these customers can expect to get. Or when I'm here, if I were to sit here and this is the place where I have my my internet, what I can get. It even takes a while to connect, so it's just kind of non-existent. It's not even connecting, so not even worth demonstrating this. It's just circling. So anyway, that's the demo. That tells the whole story, I guess. Right, so what I will do, connect the antennas and we try again. Now this thing is on auto, so if I connect it automatically detects there's an external antenna connected. So we connect both because as I want to do here is just first show the benefit you can get out of a MIMO antenna. So connect one, okay, connect the other one. I'm in a gully, so it's good, but it's not perfect. I won't get the best results I can get. So I'll do a refresh on my screen, so I'm going into the menu again. Reset the modem. I'm going to tell power off, power it on, see if it picks up a 4G signal. It's a good spot, it's just really too good. So as you can remember, my initial test, I had no antenna connected to the device. It didn't even want to connect. My RSRP was really low. Now what I get is RSRP with the antennas connected, two antennas, MIMO. RSRP is minus 108 dBm, RSRQ is minus 7 dB. So that's doable. That's not bad at all for something that is actually in a very bad spot. My speed test came up as a 30 megabits download and 5.16 upload. So from a connection that actually bombed out completely, now I have a connection that gives me actually quite decent throughput with two antennas. Now that antenna is not a no, you don't have to go over the top. The fact is you use MIMO, so you use two antennas plus minus 45 with a decent cable into your modem, and that gets you connected. That is the DR11 that's on our website. So that's I'm happy with that, definitely. Next thing would be, let's disconnect one of them, then we would go into a single antenna configuration out of this and we see how much we lose between MIMO and not having anything and then in between. Now, one of the challenges that I set myself forth in this video was to try and just show how basic design principles can be used to design antennas. Now, I don't want to bore you with the detail of the design itself because I don't think that that's always going to be your forte. So just want to give you a presentation on the flow, the thinking, and our building blocks, just like in software, if you're a software guy, so you just use different building blocks to come up with a final product. I hope to show you at the end that this dish that I showed earlier, how those little building blocks and the principles behind each of those building blocks gives you a really good antenna at the end. So the first one is, I'm back on my dipole. So this is the same dipole I showed earlier. So just have a 2.4 gig dipole. A dipole is an antenna that has it's 2 quarter wave lengths and it's fed in the middle. It creates a resonance. Now this is obviously inside the radome, so the antenna in here is much smaller than what you actually have. I use a tool. The tool we use is it's called CST Design Studio. So credit goes to that company and the tool that we use, but there are other tools as well that you can find. So similar tools. FICO is a South African company, which South African German company. HFSS is another software tool as well, but we specifically use CST for these demonstrations and also for actual design work under Blackhawk Technologies. So what I have there is a quick thing that I did. I mean, it's not even a design, it's just I know what the dimensions should be, so I build a little dipole, which is that picture in the middle. It's really just a small stubby little antenna. That's a building block for a lot of well-known common antennas. What I want to show you there is on the left, a 3D radiation pattern. Now, it is, it's called a donut shape. So, I mean, it's somehow with all the color scales, it always feels to me like it's coming out more like an apple. But whichever way, if you have a donut or an apple, it doesn't matter. So you have this structure, it radiates around it. So it just basically has this thing that it radiates energy in all omnidirectional directions around it. If you look at it from the top, there's not much happening. So it's just a ring around it. And then there's gain. There's a gain number, as you can see on the screen itself. So it says 2.26. So typically we always assume a dipole is a donut shape structure with about a 2 dB gain, which means they had the radiation if it was all around. Now it's that gain is taken and it squashes to the sides as per that balloon I showed earlier. And it has resonance or S parameter. So it shows that it's working at its best just below 2.5 gig on the plot. So that's the way the resonance is. So there's a little building block, there's an antenna, it is working, and my software tells me this thing would actually do something for me. Of course, it's not yet practical because you don't have a cable in there and all those complexities of the real life antennas is not in there yet, but that's not relevant here. We just want to show the antenna as a model. So there's the design example. Now, the beauty of tools like CST or any of those 3D simulation packages is you can look at all sorts of behavior and characteristics without, if you can't measure it, how do you know? But in simulation, you can at least study it completely, and that's the beauty of these things. So with the plot that I have here, I show E fields, so electric fields, because this thing has an electric field and a magnetic field, and this is the electric field that I'm looking at, and that's the one I always use, so E field. So on the left of the screen, there's a top view. Top view means you take the antenna, you look at it from the top, so you put it on the ground, and you look at it from the top, okay? So that's the view. You can see it's similar, and this is what I want to show you, similar to dropping a rock into water. That's the kind of behavior you can visualize it. That's how you should see these things. It starts and it circles out. So this is the wave as it just starts to circle out further and further. Now, what is path loss? This is something that I mentioned earlier. And path loss doesn't necessarily mean that you lose energy. It's just the energy that got transmitted. This rock comes in, there's a pulse. That energy has to work here, then the same amount of energy as it moves further away gets spread further over a bigger area, and that's the picture that you see there. You see how it's red. It starts with this red intense beginning at the antenna. As it goes further and further, it just goes weaker and weaker, because each of those rings, if you just want to call it a ring for lack of a better word, is say it's 1 watt. So there's 1 watt at the beginning. Then a bit later, it's 1 watt, but it's spread over a much bigger circle. Then a second later, it's much faster, but just for argument's sake, a second later, it is over this area. So this whole circle has to have the same amount of energy. So that's where path loss is significant, that's kind of the biggest contributor to what we consider path loss, is that same energy suddenly has to be spread over and over further and further areas. On the left, there's a side view, and that kind of is a 2D view of this thing. So you look at it like this. You can see it has energy going this way and it goes further, but to the top and to the bottom, not what's happening. So it just starts here and it just spreads out this way and this way and this way out. That's what this picture tries to show you. So as you can see, it's quite easy to just get a basic dipole up and running, but that's not, I mean, it's a good antenna, but it doesn't give you much more than just the basics. So the next step that I want to show you is just adding a reflector to the side of the antenna. Now, of course, the distance and the length of the reflector becomes important. In this case, it's about a quarter wave distance. The length is longer than the actual dipole itself, and when you get into this level of detail, there's actually design information available and papers that you can read, and some of classic textbooks as well. But I want to just show you how you can start to really manipulate an antenna to become something specific to what you want to do, and how this actually can improve your system significantly. So what I've done in this example that I have here, I have a dipole and I added a reflector next to it, and see what it actually does. So your gain changes from what was 2 dB, 2.26 on the previous one. Suddenly there's a gain, maximum gain of 5.19 dB. So you've added one small piece of copper or whatever material behind the dipole, and you manipulate what was initially a complete omni or radiation pattern all around in the donut shape. You start to push it forward, and you can see now on the screen here, this to the left. So if I jump to the next screen, you know the previous version of the same image you had on the left, top view was circling all around. Now you can see it's definitely more focused towards one direction on the top view, and the same now on the side view, which is when you look at it from the side, you can see there is already much more E field strength going in one direction and less going to the other direction. So you add directionality to the antenna. Gain is still the same in terms of forget about that. See, you make mistakes even when you try to explain these things. The gain is now higher to one side, but the overall energy is still the same. You're still launching that much energy, but now you are manipulating it towards one direction just by adding a reflector. Now, take it further, and I actually convert this omni into what we would call a classic Yagi or Yagi-Uda antenna, which is patented in 1926, but I mentioned that in the other video as well. Now you actually take this further, and you can go on further and further to make more, add more directors to the actual antenna itself. But in this case, you now have the reflector at the back, and you add a director to the front. You still have the original same dipole, so I didn't change the basic thing that I have. But see, now the gain has increased to 6.71 dB, gain in one direction. It's taking it from the back, so we are moving all the gain in one specific direction. If I move to the next screen, you can see where I had something that was going all around, then I started to sway more energy towards one direction. Now it's getting even more pronounced that my energy is getting much more in one direction and much less going to the back. And that is how you design antennas. That's what you do in antenna design, not how you design. This is one specific example, but that's what we do. We basically start to manipulate the radiation pattern to what we need and what we want. And then you can add all those other features like polarization. You need to look at the impedance match as well, because your VSWR would definitely change when you start to do these things close to your dipole. As I showed with my hand before, you actually start to manipulate the characteristics a bit. So you need to take everything into account. But that's what happens. That's what you want to do. Now, if I want to get to that reflector, that actual TV satellite dish concept that I showed at the beginning of the video, I first want to go back to something that you might have learned in school already. You never thought you're going to use it again in algebra, and that's the parabola. It's basically that shape where you have something that focuses all the energy, or there's a focal point. So let's go to my screen here. In school you learn a parabola was something like this, and they also had a focal point. So there was all sorts of stuff that we had to do there in school where you had that, and then basically you drew this whole curve with that in mind. but it's not just a curve that you learn about in school. It's actually used a lot, and there's many applications as well. So just your dishes that you see everywhere around has a parabolic shape or parabola. So what we use in antenna engineering is you have your parabola there, and we know there is a focal point there, for instance, just as an example. How we use it is we know that a ray comes in and it bounces, it goes through there, but it still goes on, of course. And then everything we do has a path that goes through the same point. Wherever we go, there's always a point going through the focal point. Just happens to be that way. And this is where reciprocity becomes really useful as well. So that area there is our focal point, and the focal point means that if you put something there, it will pick up everything that the dish is able to reflect to that point. A very simplistic way to explain it, a very basic way to say how this happens, but if you understand the basics, you can do something, and once you do something, you can become a specialist and get better and better at it. So by starting with the very basic explanation, you actually do get the opportunity to expand on that, but this is where it all starts, is with a very simple one. Now with the theory of reciprocity, the same applies. If you were to have a source here, so suddenly, let's make this a source just for another color. So now I'm sending something, and rather than saying I'm receiving like I've done in these examples, I receive. Reciprocity works exactly the same way, just the opposite way around. So now, let's say I make blue. So I'm sending. Same idea. So it all goes to the same direction. So wherever direction this antenna sends to, now everything that bounces from the reflector goes that way. And that, in very basic essence, is how a dish works. Very simple, extremely effective. Let me show you on the computer. Now, I have, first of all, just wanted to show this concept, like that wave thing. So I've done in CST just basically a plane wave. So plane wave means it's just a signal coming in and it's just traveling. So if you are far away, say a TV antenna, that by the time it hits you, it's just so flat. It's a plane wave. It comes and it just comes and travels through. If you were to put a dish in there, so just put a parabolic dish, you see what happens to that wave as it travels. So this is now just a traveling wave coming through. Suddenly, I've taken that shape, just a parabola, sorry, the word is wrong, put that in there. See, it's coming down. Now you see funky waves and stuff looking like there's a wavy shape happening as well. That's because you have interference, because now there's a wave coming in and coming back, which comes back to that whole standing wave effect that you have. So just focus on the wave coming in and that hotspot. So you see a hotspot. That hotspot is the focal point. The focal point shows you that is the place where you want to put another antenna, and that antenna is going to pick up that green level of E field. So in other words, much stronger signal. So the focal point is where you would want your parabolic dish to have its antenna of some sort. Now, why I showed you this antenna, this dipole with a reflector and a director, is that actually is a nice little feed antenna. So that antenna, as such, I am putting in the focal point of a dish, and I just want to show you what kind of end result you get. Remember that this antenna by itself was a 2 dB antenna. It's a donut. It sends everywhere. It's not a great signal going anywhere, but it's going everywhere. So that's basically, in a very basic nutshell, what it is. It's a good antenna, goes everywhere, but not good. It just does the basics. So that's on the table. That's my reference. I'm just putting it there so you can see it. There it is. That's what I started off with. I added the reflector, I added the director to the antenna, so it became much more directional. Now, I put that thing in front of a parabolic dish. That's what starts to happen. So first, you can see in my picture, there's the antenna that I created by those 3 building blocks. I put it in that area there. So you can see there's a small blue cube. So that's just the numerical technique that I use in CST, so I can put it in there. So that's the space where I put it. That's the focal point for this dish that I created. And I'm just showing now in my in my E-field view of the same thing using the same scale, you can see it's sending towards this dish, towards that dish, and then that whole structure is now propagating the energy out. All good and well. What does it mean? Have a look at this. So remember, I started off with a 2 dB little dipole. I made it a 6 dB Yagi antenna by just adding those components at the front and behind. I put it in front of a dish. This antenna now has 26 dB gain. Just by doing all those bits and pieces, adding a lot of metal around my antenna to come up with an antenna that looks like this. So that's how you take a very basic antenna, adding all the knowledgeable components around it to create an antenna. And you can see it's what we call a pencil beam there. Pencil beam means it's highly directional. So you're really focusing all the energy in that one particular direction. So you can think the reach is significantly more, because in a very thumbs up rule, about 6 dB gain gives you about double distance. Comes back to that calculation with path loss that I mentioned earlier, and how important and how useful it is. So this thing is going to reach so much further than what your dipole would have. Now do remember, it reaches that much further in that pencil beam direction. So well, bang, there, I could see a lot there. But behind me, if I could see something with my dipole, now there's no way I'm going to see anything, because I'm just cutting everything off from the back, and I'm saying, I just want to look at this. And that's essentially what happens. That's really it. That is, in a nutshell, that's the design example I wanted to go through. Now, of course, me being me, I did a bit more, and I'm going to show you this, but just have a look. So, with the TV antennas, they don't have this perfect shape with a perfectly centered antenna, or it doesn't look like it. It's because they're actually using an offset reflector. So for practical reasons, for mechanical reasons, it can be so much easier to actually use an offset reflector, which is you have a thing here, just have one arm to support your antenna. There's many reasons for that. So mechanical is often a dominant feature or reason why you don't want to do that, but that's all good. So what I've done, I just cut half of the parabolic shape off, the parabol. It's just half of what it was. Now, as I showed in my little picture, wave comes in and it still goes to the focal point. So even if you just look at half the dish, that physics is still going to remain, because it still has that coming to the same point. So your point doesn't change. You do have to manipulate the orientation a bit, because it's pointless for an antenna that's first here to just send to the bottom. So you do tilt it a little bit, and that's what I show in my picture there, that it is tilted a little bit towards what's left of my original dish, and you still get the same idea that the field transmits into this surface. The surface reflects it forward, and I did lose from what I had before was 26 dB. I have 22 dB, but again, I'm not going to complain. There's a 2 dB dipole converted into an overall system that now gives me 22 dB in the forward direction. I'm happy. But as you know, the final dish, which I show there, top left, typical TV antenna, it doesn't look like this half moon. It's not this half cut dish. It actually looks like a nice shape. There would be a lot more specialist design criteria into the exact shape. I've done it quite simplistically here, but for the sake of showing, I just took that half dish that I had. So I had a complete circle. I cut it in half, so you had a half dish. Then I took the half and said, okay, let's just make a circle cut out of that. I know the physics still stays, that it's still going to point towards the center point. I kept my feed as it is. There's the field. You could see the field is still showing, it's still transmitting into the circular shape. At the end, with all the cutting away to make it more practical, I end up with an antenna that is now 17.5 dB gain. Of course, it's 10 dB lower than the perfect ideal dish, but nobody wants a big 1.2 meter dish on their roof if they want TV antennas. You want something smaller, so you have to come to a compromise. That's why cell phones don't have external antennas anymore. We come to a compromised outcome, matching the customer's expectations, plus try to get the technical expectations working good enough as well. But again, I'm just saying, there's a little dipole, add a reflector, add a director, put it in front of a dish, make the dish look like something we can actually use in real life, you have a 17.5 dB gain and you have a highly directional antenna. So there's actually a recipe for my next video on what I'm going to do at RF Shop, because the idea is we bought that dish that I showed earlier on Gumtree last week for $10. So for $10, a bit of antenna ingenuity and you can make something that is as good as this. That's it. I do thank you for looking or following this video. I hope it wasn't too long. I had a lot of fun making this, and I hope you will have a lot of fun digesting everything that I have said. If you have any questions, I'm just going to skip straight through to the last one. Feel free to contact me. My email address is david@rfshop.com.au, or do ask your lecturer to get hold of me. As a favor, this is the very last one, I'm just dropping it in there. Have a look at our YouTube channel. That's just, I'm always looking for subscribers and I'm looking for content. So if you have any questions and suggestions as a student or as a student of antenna engineering, any contents would be welcome. We are creating 2 channels. One channel is the Black Spot project, where I'm kind of helping people getting connected in better ways to the internet, finding ways through the, and it's showing them on the channel. The other way is, this is the first one of a whole series I'm going to do, the art of antennas, which is just thinking of trying to present the world and you as a student for the first, as a first audience, what can be done to understand antennas, how to make them better and to use them properly. So thanks for watching, and well, good luck with your studies, and I hope you you enjoy engineering when you go out into the field. So cheers.